All right, hello everyone, and welcome back. Today we're going to talk about public good provision. So this is going to be application number 3, and we're going to study a very simple example using game theory. And the goal is going to be to show that we can often have cases of under provision of public good, and we are going to face a free rider problem. So let's illustrate this with a simple example. So suppose we have 3 players. And you can think of 3 players as 3 roommates, and their goal is to acquire a used TV that costs $90. This is just an example of any public good you can think of. This could be investment in, roads, public schooling. This could be any public good that you can imagine, but here we're going to consider that it's going to be a used TV. And the idea is that every player gets the benefit of the public good, but not every player needs to contribute. So here, the players will purchase the TV as long as at least 2 players contribute to the purchase, right? So if 2 or 3 players contribute, they're going to buy the TV. If only 1 player contributes, they're not going to buy the TV. And all players are going to benefit. And the goal is to host a Super Bowl watching party, especially to get the most of Rihanna's opening concert. And so each player has a monetary utility of $45. Okay, so it's the idea that their benefit of acquiring the TV is evaluated at $45 each. So let's think about the payoff structure of this game. So first, notice that we're going to use a normal form representation. So here, because we have 2 players, it's not going to be a 2x2 matrix, but it's going to be 2 2x2 matrices, because each player is going to have 2 actions. They can either contribute, denoted by C, or choose not to contribute, denoted by D. You can think as D to defect. And player 1 is going to be our row player. Player 1 can either defect or contribute. Player 2 is going to be the column player. Player 2 can either defect or contribute. And player 3 here is going to be our matrix player, in the sense that player 3 chooses to either play with the left matrix or the right matrix. Okay? If they play with the left matrix, they choose to contribute. If they play with the right matrix, they choose to defect. Okay? So let's compute the payoffs. So here the payoff structure is going to be of the form U1, U2, U3, where the first entry is going to be the payoff of player 1, the second entry is going to be the payoff of player 2, and the third entry is going to be the payoff of player 3. Okay, and utility is going to be linear in the net monetary benefit of each player. Okay, so let's take the case where, for example, here, player 2 and player 1 defect while player 3 contribute. What is happening here? Only 1 player contributes, so the TV is not going to be purchased. And so if the TV is not purchased, no player is getting any positive benefit, because no one is spending money, but no one is getting to watch the Super Bowl. So this is going to be the case as long as 2 players defect. So if player 1 and player 2 defect, we're also going to be in this situation here, right? But it's also true if player 3 defects here, and if player 1 or player 2, so we would be here, defects, and the other player contributes. Okay, so here, if player 1 defects and player 3 defects and player 1 contributes, we still have no purchase. If player 1 contributes, player 2 defects, and player 3 defects, we still have no purchase. Okay, so all of these cases, we don't purchase the TV. In the case where player 1 contributes, player 2 contributes, and player 3 contributes, all 3 players are purchasing the TV. They're splitting the cost equally, so they're each paying $30, and they're getting a monetary benefit of 15, which is the net amount 45 minus 30. Okay? Now, if instead player 1 chose to defect, while player 2 and player 3 contribute. Here, player 1 is the free rider, because player 1 gets a benefit of 45 without facing any cost. Player 2 and player 3 are both contributing half of the cost, so $45, and they're getting a benefit of $45, so in net, they're getting a benefit of 0. Here, what happens if instead player 1 contributes, player 3 contributes, and player 2 defects? This time player 2 is a free rider. So player 1 is getting a net benefit of 0. Player 2 is getting a net benefit of 45 because they get the benefit of the public good without any contribution, and player 3 gets the benefit of 0. And finally, what is happening when player 1 and player 2 contribute, but player 3 is the free rider? In this case, we're also in a case where player 1 and player 2 are contributing $45 and getting a benefit of $45. So on net, they're indifferent, and player 3 is getting the whole benefit without any of the cost. All right, so this is going to be a payoff structure. So now we're going to consider the best response of each player by fixing the strategy of the other players, and this will allow us to find the Nash equilibria of this game, of which there are many. Okay, so let's start with player 1. Okay, so we're going to fix the strategies of the other players. So suppose player 2 plays D and player 3 plays C. Player 1 is comparing the payoff here and the payoff here, and they're going to be indifferent between the two. So player 1 is indifferent between the two, so we underline the two because each are our best response. Now, suppose player 2 defects and player 2 contributes and player 3 contributes. Here, player 1 is going to compare 45 and 15. And because 45 is greater than 15, player 1 is going to prefer to defect. They're much better off getting the public good for free and free riding on player 2 and player 3's contribution. And here, similarly, we can do the same on the right matrix, but here, whatever the other two players play, because player 3 is defecting and player 2 either defects or contributes, if they contribute, they get a TV, but they have to pay $45 for it, so they're indifferent between contributing and not contributing. So here, both defecting and contributing are going to be best responses for player 1. Now we're going to do the same for player 2. So let's fix the strategy of player 1 and player 3 here. And player 2 is going to compare the payoff from defecting and the payoff from contributing. And here player 2 is going to be indifferent, right? If we fix the strategies of player 1 and player 3 to being player 1 contributes and player 3 contributes, here player 2 compares defecting and contributing, and once again, it's in their best interest to free ride and to defect, okay? So we can do the same for the right matrix, but this time player 2 is indifferent. And finally, we can do the same for player 3. So for player 3, we're going to compare the left and the right matrix for fixing the strategies of the other two players, so player 1 and player 2. So if player 1 and player 2 both defect, player 3 is indifferent between contributing on the left matrix and defecting on the right matrix. If instead player 1 contributes and player 2 defects, right, then player 3 is comparing 0 here by contributing and 0 here. And they're also going to be indifferent. Now let's jump straight to the interesting case. If player 1 contributes and player 2 contributes, player 3 is comparing 15 here and 45. And player 3 prefers, of course, to defect and free ride. Okay? And the last one is a case where player 2 contributes and player 3 defects, and here player 3 is indifferent. All right, so when we find the best response of each player in pure strategies, whichever outcome which is underlined for all three players, which is a best response for all three players, is going to be a Nash equilibria. So here we have a lot of Nash equilibria in pure strategies. And we have two types of Nash equilibria. I'm going to highlight them in color. So our first type of Nash equilibria in pink is the Nash equilibria where not enough players are contributing. All right. So they're not going to purchase the TV because not enough players are choosing to contribute. And in the end, everyone has a payoff of 0. The second type of Nash equilibria are those where we have a free rider. So where two players contribute and are indifferent between contributing and not contributing, and a third player is free riding on the contribution of the other two players. So the pink Nash equilibria highlight the issue of underprovision of the public good. We could be in an equilibrium where the public good is not provided despite the fact that everyone would be better off if it was provided. And the orange Nash equilibria highlight the free rider problem. If enough people contribute to the public good, I'm much better off free riding than contributing myself and sharing the burden with the other contributors. So that's it for today. Notice one last thing is that when you write out the Nash equilibria, you have to write out the strategies. So for example, for this Nash equilibria, the Nash equilibria is going to be D, C, and D, denoting the fact that player 1 is deviating, player 2 is contributing, and player 3 is deviating. Okay? And finally, as an exercise, I'm going to leave you with changing one parameter of the game, changing the monetary benefit to 40. And if you do everything right, you should see that only the pink Nash equilibria will survive, and we won't even have free riding Nash equilibria where the public good is provided. We would have a case where the public good is never provided. All right, that's it for today. Thanks a lot for your attention.